Hello everyone, welcome to the 30th episode of this series. In this video, we'll talk about eigenbases. So in the last few episodes, we have learned about a few subspaces of Rn, and we've learned how to investigate them to find at least one of their bases and their dimension. So in this episode, I want to focus on a particular type of basis called an eigenbasis, and we'll start by a motivation. So let A be a matrix. We can then simplify multiplication by A. That is, we can simplify the action of the linear transformation corresponding to the matrix A. So note that the action on any vector can be reduced to the action on a basis. In other words, using linear combinations, if any vector W can be written as a linear combination of V1, V2 through Vn with coefficients C1, C2 through Cn, then A times W is going to be C1A V1 plus C2A V2 dot plus CNA Vn. So we've just we've just distributed A to all of the vectors. And we do know that matrices, when they multiply with their eigenvectors, they do so in a very simple way. In other words, they just multiply the input vector by a scalar, which essentially is, the eigenvalue. So we can simplify a matrix multiplication using a basis of eigenvectors called an eigenbasis. And that essentially is the definition. An eigenbasis for an n by n matrix A is a basis for Rn consisting of eigenvectors of A. So let's look at an exercise. So we're given a set of three vectors in R3, and we're given a 3 by 3 matrix A. And the question is, do these vectors form an eigenbasis for A? So we need to check that S is a basis of R3 and that every element of S is an eigenvector of A. This is just by the definition of an eigenbasis. So to show that S is a basis of R3, we only need to check that S is linearly independent because S already has three elements. And if you remember the 2 out of 3 rule, it said that when you have the correct number of vectors, you can either show that S is linearly independent or it's a spanning set. So we're going to go with linear independence because it's easier. So we will put these three vectors in a concatenated matrix and then reduce them to find their row echelon form. And since every column has a leading one, that tells us that these vectors are indeed linearly independent. So as a result, S is actually a basis of R3. And the next part is to verify that the vectors in S are indeed eigenvectors of the matrix A. And that is easy to verify because all we need to do is to multiply these vectors by the matrix A. And if the resultant vectors are multiples of the original vectors, then those vectors are eigenvectors with eigenvalue equal to the multiple or to the ratio. So we see that it happens for all three of them. Therefore, all three of them are indeed eigenvectors of A, and because they form a basis, the three vectors actually form an eigenbasis of A. Okay, so let's look at an observation relating matrix multiplication and eigenbases. So let V1 through Vn be an eigenbasis for A. That is, these vectors, are a basis for Rn, and each of these vectors are also an eigenvector for A with corresponding eigenvalue. If W is a linear combination of these vectors V1 through Vn with coefficients C1 through Cn, then we saw earlier that A times W is just C1 times AV1 plus C2 times AV2 plus C3 times AV3 dot 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 till Cn times AVn. But because now V1 through Vn are eigenvectors, A times Vi becomes very simple. It's just lambda I Vi. So we get this term. But now if you have any other power of A, using the fact that A to the n multiplied with an eigenvector V is just lambda to the n uh, times the vector V, we get these much more simplified results. So instead of doing lots of matrix vector multiplications, we're just doing lots of scalar multiplications, and that is a lot easier. So let's look at an exercise to demonstrate this. So we're given a matrix A, and we're given a vector 1, 1, 1. And we also know that 1, 1, 1 can be written as a linear combination of these vectors 1, 0, 0, 0, minus 2, 1, and 2, minus 1, 1. And we want to compute a to the 100 times the vector 1, 1, 1. Now, from exercise 1, we know that these three vectors are actually eigenvectors of A with eigenvalues 2, 2, and 3 respectively. And therefore, using our observation that we just saw, we can compute this quantity in the following manner. So we first write 1, 1, 1 as its linear combination. We multiply A to the 100 to each of them. And now, because each of these are eigenvectors, we just replace A to the n with lambda to the n, the corresponding lambda. And that gives us this thing as a final answer. Now, the last thing I want to say is that eigenbases don't always exist, as the following example suggests. So the matrix B, given by entries 2, 3, 0, 2, does not have an eigenbasis. And this happens because its characteristic polynomial, PBX, can be computed to be x minus 2 whole squared, which only gives us 2 as the eigenvalue. So there's only one eigenvalue, and that's 2. But that's not the breaking point. The problem is that when you compute the two eigenspace, we get that it's the collection of all vectors of the form T0, where T is in R. So the problem now is that this collection is one-dimensional in nature because any two vectors of E to A are multiples of each other. So only one vector from this eigenspace could be in a potential eigenbasis, because if there are two of them, then you don't have linear independence. So since there is no other eigenspace to choose vectors from, and this matrix is 2 by 2, you can only have a potential eigenbasis with just one vector, but then it's not an eigenbasis because it's not a basis, because you need exactly two vectors. Okay, and with this, I would like to end this episode. Hopefully things were clear. I'll see you guys soon. Up until then, happy learning.